Hey everybody, Dr. A here, and in this video we're going to be exploring an example of how to evaluate a steel bolted connection. And we're going to be referencing the AISC Steel Construction Manual 16th edition as we go through this. So make sure you have a copy of that, either your hard copy of your 16th edition steel manual or a PDF, and follow along with us as we go through this process step by step. Additionally, this example is quite similar to example 7.2 in the Segui and Soleimani Steel Design textbook, 7th edition. So if you have a copy of that textbook and you want to see a similarly set up example, that's going to be similar to example 7.2. This is, I put my own twist on the example, so I'm not, redoing that exact example, but it's quite similar to that if you want to follow along with another reference. So let's go ahead and get started. We're being asked to determine the connection strength based on bearing and shear. Now, what we're given here is a tension member. It looks like it's a plate with a 1/2 inch thickness and a width of 2.5 inches, and it's connected to a gusset plate. We see this gusset plate in blue here that has a thickness of 3/8 of an inch, and it's connected by 2 bolts. So the 2 bolts have a center to center spacing of 3 inches, and we have a center to edge spacing of 1.5 inches on either side of those bolts. Now, what materials are we dealing with here? Well, we're being told that we've got A36 steel, and we can assume that that's going to be A36 steel for both the tension member and the gusset plate because there's nothing that tells us otherwise. So if you recall, A36 steel has a yield stress F sub Y of 36 KSI, and we're going to use an ultimate tensile strength of 58 KSI. That's the F sub U value. And we can remind ourselves of those values from table 2-4 in the Steel Construction Manual. So if you want to make sure you know where to go, pause the video. We're in table 2-4 to get the properties of A36 steel. We have 3/4 inch diameter A307 bolts. We have standard holes, and we're being told to use LRFD. So let's go ahead and get started. I'm going to turn the page here, and under solution, I've listed out a few important things so far. Again, we're referencing the AISC Steel Construction Manual 16th edition. Mostly, we're going to be within section J3. So if you're following along in your steel manual, you want to pause the video, go to section J3 in your steel manual, because that's where we're going to be most of the time in this example. We need to check a couple of limit states per the directions. We need to check bearing strength, and then we need to check shear strength of the connection. Let's talk about bearing strength first. So when we're checking bearing strength, we're going to be in section J311, okay? J311. And we're going to check 2 sublimit states within the bearing strength limit state. We're going to check general bearing, which is given as equation J36A, and then we're going to check tearout, which is given as equation J36C, okay? So again, follow along in that steel manual to make sure we're looking at the same thing. So if I go to J36A, that equation, that's going to be R sub N equals 2.4 dt F sub U. And then if I go to equation J36C on the next page in your steel manual, that's going to be given as the nominal strength is Rn equals 1.2 L sub C times T times F sub U, okay? And so one more time, what do these values mean? Well, F sub U is that ultimate tensile strength. Again, that's back in the Steel Construction Manual, table 2-4 at the very beginning of the manual. That's going to be 58 KSI. So if you want to make a note here, maybe in purple, this is 58 KSI. Also, this is 58 KSI, all right? What about this D value right here? This D value is going to be the whole the fastener diameter, the bolt diameter. So that this D value is that 3/4 inch diameter that was given here, okay? So we'll make a note of that. This D value right here is 3/4 of an inch. All right. What about T? What about this T value? Well, T is the thickness of the thinner connected part. All right. So if we look back in the original diagram, if T is the thickness of the thinner connected part, that means the thinner of the member itself and the gusset plate, what should we take as T? Should it be 1/2? No, it should be 3/8 because the gusset is thinner than the connected member. So we're going to say since the gusset is the thinner connected member, its thickness controls. So this is what that T is. T is going to be equal to 3/8 of an inch in both of these calculations. So we can put that up here, 3/8 of an inch and 3/8 of an inch here, okay? Now, what about L sub C? What about this L sub C? Well, this is a clear distance in the direction of the force between the hole edge and either the edge of the adjacent hole or the edge of the material. So we're going to have to show a little bit of work here, and we're going to do that on the next slide, on the next page, okay? So let's turn the page and do these calculations together, all right? So I'm going to go back to this color blue here, and I'm going to say, you know, for bearing, we had Rn equals 2.4 dt F sub u, and we know all of these values. This is 2.4 times 3/4 inch diameter bolt. We wrote that on the previous page, times 3/8 of an inch gusset plate thickness, times 58 KSI ultimate strength, okay? So crank this through in your calculators, and you should get a nominal strength of about 39.15 kips, okay? So that's an important value. That's not the end of the story, though. That's just for bearing. We also need to investigate that tear-out limit state, okay? Now, when we look at tear-out, we need to look at two parts that could tear out, okay? We need to look at tear-out between the bolt and the edge, and we also need to look at tear-out between the bolt holes, okay? And we notice that we have some different distances there. We have a 1.5 inch distance, and then we have a 3-inch distance in between the bolt holes. So for tear out, I'm going to make a note here, and I'm going to say, let's do it in red. I'm going to say investigate edge to hole and hole to hole tear out, okay? And again, those distances are different. One's 1.5 inches and one is 3 inches. So we actually need to evaluate the tear out potential 2 times, okay? So what is our tear out nominal strength? Well, we wrote that on the previous page. That's Rn is 1.2 times L sub C T times F sub U. And so what's really going to change here between edge to edge and hole to hole tear out is L sub C, okay? We already said T is 3/8 of an inch and F sub U is 58 KSI, right? So we know T and we know F sub U, but we need L sub C, all right? So let's go ahead and investigate L sub C more specifically. So first, I'm going to say, I'm going to look at edge to hole, all right? And so here, if you're looking at your steel manual, it says L sub C is the clear distance in the direction of the force between the edge of the hole and the edge of the adjacent hole or the edge of the material, okay? So if we're looking at edge to hole, remember, we're not looking at center to center distance, we're looking at the edge of the hole to the edge of the material for edge to hole, okay? So how do I calculate that L sub C? Well, in this case, L sub C is going to be 1.5 inches minus d whole over 2, okay? So if I'm looking at, here's the edge of the material, okay? And here is that is an ugly bolt hole. Here's that bolt hole. I'm looking at this distance right here, L sub C, okay? So how do I get that? Well, this has to do with the hole diameter, not the bolt diameter, okay? So how do I get the hole diameter? Well, I get D sub hole from table J33, okay? And so if I go to my steel manual and I go to table J33, flipping my steel manual right now, when I have a bolt diameter of 3/4 of an inch, then my hole diameter for a standard hole is going to be 13/16 of an inch, okay? And again, that's table J33 using a bolt diameter of 3/4 of an inch with a standard hole. So the diameter of the hole is 13/16 of an inch, okay? And so if I need that L sub C now, I can say L sub C equals that 1.5 inch distance minus 13/16 of an inch over 2, right? Because this right here is 13/16, and this distance from the center of the hole to the edge was the 1.5 inches, okay? So again, to the center of the hole to the edge is 1.5 distance. So when I crank that through in my calculator, I should get approximately 1.094 inches, okay? And so finally, I can get that R sub n value as 1.2 times 1.094 inches times the thickness, which is 3/8 of an inch. That's the gusset plate thickness, times 58 KSI. And I'll punch all that through, and I should get about 28.55 kips. Okay, so that's an important value. Now I need to investigate the hole to hole distance. Okay, so again, I just did the edge to hole. Now I need the hole to hole distance. Okay, and in this case, L sub C is going to be 3 inches minus just the diameter of the hole. And the reason for that is, if I draw the sketch over here, I've got these two holes, and you know, I have the center to center spacing is 3 inches. And so what I'm doing is I'm subtracting a D hole over 2 and another D hole over 2. And so what I'm left with is this 3 inches minus D hole. I know that's not my best artwork, okay? But that's how I get that L sub C. And so if I punch this through really quickly, I should get about 2.188 inches for that L sub C, because again, that D hole is 13/16, okay? Same as the D hole is what it is. The diameter of the hole is what it is. And so finally, I can run through this Rn equation again for tear out. 1.2 times 2.188 inches times 3/8 of an inch times 58 KSI. And I get a nominal strength between the holes for tear out as 57.11 kips, okay? So looking at what I have here, I have 3 potential strengths here, okay? I've got general bearing strength, which is 39.15 kips. I've got the tear out strength from the edge of the material to the edge of the hole is 28.55 kips. And then I've got the tear out strength between the holes is 57.11 kips, okay? Now, that's bearing and tear out, which again, bearing and tear out are both subsets of the concept of bearing, okay? In fact, remember, tear out is really a result of excessive bearing when you look at the edge distances between a hole and either another hole or the edge of the material. Now, we also need to check the shear strength, okay? So I'm going to turn the page here, and we're going to say shear strength is governed by equation J31, okay? So if you flip the page a little bit and you go to equation J31, we have the following governing equation for shear strength. We have Rn equals Fn times the area of the bolt. And this is the cross-section area of the bolt, okay? Cross-section area of the bolt. And F sub n is a nominal tensile strength. And for shear, we're going to say F sub n is actually equal to F sub nv from table J3.2 in your steel manual, okay? So if I flip my pages in the steel manual, a couple pages, and I go to table J3.2, we're going to say for A307 bolts, we see in that table that FNV is 27 KSI, okay? Now, you might be looking at that table and you might say, well, wait a second, there's two of them. There's 227 KSIs there, right? So if you notice those columns in table J32, one of them says threads not excluded from shear planes and threads excluded from shear planes, okay? So what does that mean? Well, what that means is if I have a bolt, let's change colors here to black real quick. Let's say that I have a bolt here. I'm going to draw this kind of bolt head there. That is an ugly bolt head. Let me try to draw that a little bit better for you. Okay. So there's a bolt head, and this is the shank of the bolt, okay? That's what we call the shank of the bolt. And the bolt has threads here, right? Where the bolt kind of screws in to a bolt hole, okay? So if the shear plane is maybe somewhere up here, okay, above the threads, then this is what the table would label as that capital N. If you're looking at table J32, this is threads not excluded. I'm sorry, this is, I said that the opposite. This is X. This is threads excluded from the shear planes, okay? Excluded from the shear planes is this case. Almost said the opposite, but I caught myself. Now, if the threads in the bolt were situated such that here was your shear plane, okay? So the shear plane goes through the threads, then this is the column in table J32 labeled threads not excluded from shear planes, okay? So the N means the threads are not excluded, which I know that's kind of a weird way to say it. It might make you think the opposite, like I almost got caught doing just now. But threads not excluded from the shear plane means that the threads are crossing the shear plane, or vice versa. The shear plane crosses the threads, okay? So you would use that column. If you had the threads are excluded from the shear planes, which means that this shear plane where the shear force is slicing is not crossing through the threads, that's the X column in table J32. Now for A307 bolts, it doesn't matter, right? It's 27 KSI, no matter how you look at it, right? But for other types of fasteners that you might use that are in that table J32, like group 120, group 144, group 150, group 200 bolts. The values are different, right? If you're looking in the steel manual along with me, then you see that you have different values for FNV, whether you have threads not excluded N or threads excluded X. So you just got to be careful with that. Maybe take a pencil or a highlighter and make a note of that in your steel manual so you don't accidentally miss that later on. But that's what that means, okay? So, so what do I do next? Well, I need the area of the bolt, the cross-section area of the unthreaded part of the bolt. So all we know is, A sub B is going to be pi times the bolt diameter squared, which is 3/4 of an inch squared over 4. I think our bolts were 3/4 of an inch, right? Let me scroll back and check. Yep, 3/4 of an inch, A307 bolts. And so if I punch that in my calculator, I should get about 0.4418 square inches. And then all I need to do is calculate that shear strength Rn, nominal shear strength Rn. And I'm going to say that that's, 27 KSI times the 0.4418 square inches. And when you punch that through, you should get about 11.93 kips. Okay. Now, how does this compare to bearing and tear out? Well, it's a lot less than bearing and tear out, right? Bearing and tear out were 39 kips of strength, almost 29 kips of strength, 57 kips of strength, and shear strength is 11.9 kips of strength. So we're going to say since Rn for shear is less than bearing and tear out, it controls. All right. Now we have two bolts, right? This force has to shear through two of these bolts. So how do we handle that? Well, this value, 11.93 kips, is for one bolt. So what we do now is we say our design strength is phi Rn, and that phi factor is 0.75 times 2 bolts times 11.93 kips of strength per bolt, because that 11.93 kips was for one single bolt. And so we can crank this through, and we should get, let's see what we get, 0.75 times 2 times 11.93. So I get about 17.9 kips of strength, and that is my connection strength based on shear and bearing for the bolts themselves, okay? And just to make a little note here, this 0.75, this is phi, and this is given in J3.7. If you're following along in the steel manual, you see that J3.7 phi is 0.75. Now, am I done? Well, pretty much I'm done with the strength, but we always need to check bolt spacing and edge distance requirements, okay? And so that's going to come from sections J34, J35, and J36. So let's do that together. In J34 in the steel manual, you have minimum spacing, okay? The center minimum spacing, according to J34, is 2 2/3 times the nominal bolt diameter, okay? So that's going to be equal to 2.67 times 3/4 of an inch. So that's the bolt diameter, not the hole diameter. Remember, the hole diameter was 13/16. So we need the bolt diameter, all right? So if I punch this through, 2 2/3 is 2.67 times 0.75. I get a minimum center to center spacing of 2 inches. That means that your center to center spacing has to be 2 inches or bigger. So we have, this is less than the spacing that we have, which is 3 inches. So we're good to go. Our center to center spacing was 3 inches. So we're good on that. We also have the, the clear minimum distance is just minimum of D. Okay, so it says in J34, the clear distance between bolt holes or slots shall not be less than D. So again, you know, this is 3/4 of an inch. And what is our clear distance? Well, our S clear was equal to, we calculated that a couple pages ago. Our clear distance L sub C was 2.188 between bolt holes, okay? So we can make that note here. That was 2.188 inches, so we're good to go there, okay? What about J35? That's the minimum edge distance, okay? It refers us to table J34, which is on the same page of the steel manual. So for a bolt diameter of 3/4 of an inch, our minimum edge distance is equal to 1 inch, which is less than S center edge that was provided of 1.5 inches. So we're good to go there. All right, and then J36 checks maximum spacing and edge distances. So S max is 12 times the minimum thickness. The minimum thickness was 3/8 of an inch. That's the minimum thickness of the connected parts, which was our gusset plate. So 12 times 3/8 is 4.5 inches, which is less than 6 inches, which is still bigger than the maximum allowable distance of 1.5 inches. And again, that reads the maximum distance from the center of any bolt hole to the nearest edge, okay? So at this point, we're good to go. We can check that off. And, you know, the problem really didn't ask for all of this, all the spacing investigation. We were pretty much done with the problem when we calculated the strength of 17.9 kips. However, in practice, you want to check all of your spacing requirements because that is part of the overall design process of these kind of simple connections. So that concludes this example. If you found this helpful, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.